talking about is reaction mechanisms. I absolutely love these. I love doing substitution. I love looking at the mechanisms to try to figure out what is consistent with the overall rate law. And so once you understand this whole idea of rate laws, and that when you look at the coefficients, it doesn't necessarily tell you how fast the reaction is going to go when you speed up a reaction. And so we want to make sure that we get a good understanding for what these mechanisms are telling us. So first thing is, what does the slowest step tell you? Well, the slowest step that you have is actually telling you your rate. It's your rate determining step. That's the one that's going to tell you how fast your reaction is going to go. It's your slow step that actually determines your rate. So a lot of times people think that it's your fastest person that determines how good you're going to do in a relay race, and that's not the case. It's actually the slowest step. So the slowest step of a reaction is called the rate determining step. Awesome. That is your rate determining step. So what we want to really look at is our slow step. And so what I like to do is I basically like to underline where my slow step is, okay, in each one of these mechanisms. And so it says the rate of this reaction, 2A plus B gives me products, is consistent with the first order kinetics. So what they're telling us is for both A and B, it's first order. So if I were to write a rate law for it, I would say rate is equal to K times A to what power? To what order? 1. Times B to what order? 1. Okay, so it's going to be rate is equal to Ka times B, which if you look at this, keep in mind that the coefficient isn't mattering to you. It's actually whatever your order is that they tell you that was determined experimentally, that's what matters. So we're going to just go from A to B to C to D, and as soon as we find one that matches this rate law where our slow step matches that, then we're good to go. Sometimes it's A, and sometimes you have to keep on going. So what we're going to do is we're going to take a look at our slow step. And what this is telling us is the rate of production of AB is equal to K times the concentration of A times, not plus, times the concentration of B. Does that match our rate law? Then it's done. Our answer is A. Okay? Let's check to see how some of these other ones work. If this is our slow step right here, what we would say for this one is the rate of production of A2 is equal to K times A, which means it's equal to what? A squared. Well, that doesn't match. If we were to look at something like this, then what we would end up saying is that the rate of our slow step, we can't use our fast step, we have to use our slow step. The rate of production of our products, they're just saying products, is equal to K times AB times A. Well, the problem is that AB is, what do you call something that is formed and then used up in the reaction? That's called an intermediate. So we know that this is actually an intermediate. And so we need to get rid of AB. We cannot have AB inside of here. We need to actually substitute something else in for AB. Well, right here, it tells us the rate of AB is equal to K times the concentration of A times the concentration of B. But that's not our slow step. If this were our slow step, then we would be okay, but it's not. It's telling us that that's our fast step. So what we need to do is we need to substitute AB in for AB right there. So we're going to take all of this and we're going to put it right inside of there. And so what we get is the rate of this is equal to K times K, which we're just going to call what? K prime. And then we're going to multiply times A times B, and then don't forget times this A again, because that A is still there. So we just took this and we stuck it in for there. So now this part is representing that right there, times A. So what is this actually equal to? K prime times A squared times B, which also is not consistent, okay? So obviously this one's not going to work as well. So let's move on and let's check to see if we can do another one. And the more examples you do of this, the better you're going to be, okay? So you always have to find your slow step, and if your slow step is not the first step, you have to substitute in because you've got an intermediate there, and or a catalyst, okay? So they're giving us this reaction, and it says that it's found to be second order with respect to NO2 and zero order with respect to CO. So how would you write your rate law? You would say that the rate is equal to what? K times NO2 squared times CO to the 0 power, which is equal to 1. So we don't have to write that one down, okay? So we're going to leave that one out. So here's my slow step right here, and it's my first step that's written. So I don't even have to worry about going to my second line, okay? You can only substitute from the bottom, like the top can be substituted in for the next line, but you can't go the other way around. So I would not be able to substitute here my fast into my slow. You start at line 1 and you move down. So in this case here, what would my rate be equal to? Well, my rate of production of NO3 and NO, comma, I did comma NO. So the rate of production of these two is equal to K times what? NO2 times NO2, which means it's NO2 squared. Is it consistent with my rate law that's written here? Check. Yes. The overall, this mechanism is consistent with the overall rate law. Okay? So the idea is that this is figured out experimentally, and this mechanism was written, and so you try to figure out if it matches. So that's what we would write down there. What I want to make sure that we do too is we also want to show that not only is it consistent here, but that this reaction matches your stoichiometry for this, okay? And so what you do in order to do that is, so if I want to cancel things out that appear on both sides. Can you tell me what you see that cancels out on both sides here? The NO2 cancels out here and here, so one of them cancels out with one of them there. What else cancels out? The NO3 cancels out there, and is there anything else that cancels out? No. So if I were to rewrite this, I would write NO2 gas plus CO gas, then my arrow, yields NO gas plus CO2 gas. Does my stoichiometry check with the reaction as it's written? Yes. Okay. So you would say that the stoichiometry also matches the reaction that's written. Okay. And so when you write a rate law or rate mechanism, you also need to make sure that the stoichiometry works for it as well. All right, and let's take a look at number 4 down here. It says the following reaction mechanism is proposed for this reaction. And so we've got, it says, is the mechanism consistent with the overall reaction? And if so, what rate law does it predict? So the first thing we're going to do is the stoichiometry to make sure that it matches too. So if we do the stoichiometry, what cancels out? The N2O2. I'm just going to kind of like just put like a circle thing around that, there and there, just to say that those cancel out. Does anything else cancel out? No. So what I would write is NO plus NO on the left would give me 2NO gas plus the O2. And then those two canceled out, so I'm left with 2NO2 gas. And yes, that checks because that matches the stoichiometry of that. So now what we want to know is we want to know what rate law predicts. So based on our slow step, we're going to go to our slow step, not the fast step, you have to go to the slow step. And we're going to try this on your own. So now we're going to write rate of NO2, of production of NO2 is equal to K times what? N2O2 raised to the first power times O2 also raised to the first power. What's wrong with it? Why can't we leave it like this? There's an intermediate. Awesome. N2O2 is an intermediate. It does not appear in my overall reaction, which means I need to get rid of it. How do you get rid of it? Substitution. Perfect. We're going to use substitution. So let's figure this one out. So this one is the rate of N2O2 is equal to K times NO times what? NO, which means it's NO squared. So what I'm going to do is I'm going to take this and I'm going to put it where?
In for N2.
in for N2O2 right there. Awesome. So now what I get is I get K, not K, but K prime times NO squared times O2. Okay. What two requirements must be satisfied in order for the reactants to successfully form products? In other words, what are the two parts of the collision theory? Do you remember what two things need to be met in order for this to happen? One is your activation energy needs to be right. Awesome. So you have to have the right activation energy. And what was the other thing? Orientation. And the orientation of them must also be right. Okay? And we'll do more of these also, but I wanted to make sure that we got a little bit more practice with doing the substitution. Awesome. That's it for reaction mechanisms, everybody.